scalar triple product of vectors. Say scalar triple product of vectors, vector A, vector B and vector C is denoted and defined as, say notation is in a box, keep vector A comma vector B comma vector C. So in a rectangular box, in a rectangular bracket, keep vectors separated by comma, or we can also put these vectors without separated by comma. So these both symbols are allowed. So vector, a scalar triple product of three vectors, this is the notation, and definition is it is equal to, it is nothing but a dot product of vector A with B cross C. It is dot product of vector A with B cross C. So this is definition. Now see, here properties. If vector A is A1i plus B1j plus C1k, vector B is A2i plus B2j plus C2k, vector C is A3i plus B3j plus C3k. If these are vectors, then scalar triple product of these vectors or value of this dot product, it can be obtained by determinant first row A1, B1, C1, that is scalar components of vector A. Then put scalar components of vector B, that is A2, B2, C2. Then put scalar components of vector C, that is A3, B3, C3. So put in sequence components of vector A in first row, components of vector B in second row, and components of vector C in third row. As for example, suppose if vector A is 3i minus j minus 4k, vector B is I plus j plus 3k, vector C is 3j minus k. These are vectors, and we want, suppose we are asked scalar triple product of these three vectors. Question is, find scalar triple of these vectors. So whenever we want scalar triple of three vectors, scalar triple product of three vectors, we use this method, this property, because here components are given. So here scalar triple product of these three vectors is equal to, by this property, in the determinant first row 3 minus 1 minus 4, second row 1 1 3, third row, see here first component is 0, there is no vector I, so 0 3 minus 1. So it is equal to 3 into minus 1 minus 9, minus 1 minus 9, minus minus 1, that is plus 1, into minus 1 minus 0, minus 4 into 3 minus 0, that is 3. So this is equal to, see, once again we check, 3 into minus 1 minus 9 plus 1 into minus 1 minus 0 minus 4 into 3. So this is minus 10 into 3 minus 30, minus 1 minus 12. So this is minus 43. So this can be positive number, it can be also negative number. Then second property is, see here I take a parallelepiped. Suppose this is a parallelepiped. Say parallelepiped is a three-dimensional object whose which are having, you can see that here there are 6 sides. This object is having 3 pair of parallel sides. Say you can see that here front side is a parallelogram, back side is a parallelogram, left side and right side parallelogram, top and bottom are parallelogram. So 6 sides are a parallelogram. It is a parallelepiped. Volume of this parallelepiped can be found if this corner is O and this corner is formed by, this is vector A, this is vector B, and this is vector C. This corner is formed by vector A, vector B and vector C. That means if vector A, vector B and vector C are adjacent edges or adjacent sides, we can't say sides, adjacent edges of any parallelepiped, then its volume is equal to absolute value of this scalar triple product. Absolute value of that scalar triple product, that is modulus of that scalar triple product. So if volume of a parallelepiped having 3 adjacent edges, vector A, vector B and vector C, these are 3 adjacent edges, is V is equal to absolute value of this scalar triple product. It means we can say volume is modulus of this box product. So in this case we can say, suppose we are asked that question, if vector A is 3i minus j minus 4k, vector B is I plus j plus 3k, vector C is 3j minus k are adjacent edges of a parallelepiped then find its volume. So by this result, volume is, it is modulus of box product of these three vectors. Modulus of box product of these three. Say this is also said to be box product. Scalar triple product of a vectors, it is also said to be box product. I am also speaking box product. So this is formula. See, these vectors must be vectors along three adjacent edges. Now see, we have taken same vectors. So what is its value? Already here we have calculated. So this is equal to modulus of minus 43. So it is equal to 43. Fourth property is box product of vector A, vector B, vector C, or scalar triple product of these three vectors. Now see here we can rotate these vectors. See here, first vector is vector A, second vector is vector B, third vector is vector C. We are now rotating by this way. Here starting is from vector A. Now if I start from vector B, then it will be vector B, comma, vector C, comma, vector A. If I start from vector C, then vector C, comma, vector A, comma, vector B. Suppose you are given vector X, vector Z, vector Y. See, here this is given vector X, then next is vector Z, next is vector Y, and we are rotating as just we did here. See here starting was from X, now I am starting from Z. So vector Z, vector Y, vector X. Or if I start from vector Y, then vector Y, vector X, Y, then X, then Z. So we can rotate vectors by this way, maintaining the sequence. So don't disturb the sequence, keep given sequence as it is, and we can rotate in a box. Then next property is vector A, vector B, vector C, box product of these three vectors. Now here what I do, I interchange any two vectors among themselves. Suppose I am interchanging these two. So here interchanging these two, vector A, vector C, vector B. See, these two are interchanged. B and C are interchanged among themselves. That means just we discussed property, second property. In a determinant, second and third row, scalar products of second and third vector in determinant are interchanged. So value of new determinant becomes additive inverse of given determinant. So this will be additive inverse of this determinant. Suppose vector A, vector B, vector C. If I interchange these two vectors only, so again it new will be additive inverse of previous one, B, A, C. So here if we don't keep comma, then also allowed. If you keep comma, then also allowed. Then sixth property, if I repeat vectors, Suppose these two vectors are repeated. Repetition of vectors in a box, that means two lines, two rows are identical, indeterminate. So its value is 0. If here I keep vector A, vector B, vector A, vectors repeated, so value is 0. Then one more property based on this scalar triple product. See, it is a theorem. Three vectors A, B and C. Three vectors are coplanar if and only if. Three vectors are coplanar if and only if their vector triple product is 0. If vector triple product is 0, vectors are coplanar. If this is non-zero, that means these three vectors can form a parallelopipe. So this property can also be written as box product of these vectors is 0. Find lambda if these vectors are coplanar. So here we take vector A is vector I minus j plus k. B is 3i plus j plus 2k. And vector C is I plus lambda j minus 3k. We take these symbols. Given that these vectors are coplanar. Now just to discuss, if vectors are coplanar, then their box product is 0. Box product of these three vectors is 0, or scalar triple product of these three vectors is 0. So therefore, determinant components of vector A in first row, it is 1, minus 1, 1. Components of a second vector in second row, 3, 1, 2. Components of third vector, 1, lambda minus 3. This is equal to 0. Given that vectors are coplanar, so take equal to 0. If you are asked that prove that vectors are coplanar, then prove LHS equal to 0. So therefore 1 into minus 3 minus 2 lambda, then minus plus 1 into minus 9 minus 2 plus 1 into 3 lambda minus 1 equal to 0. So 1 into minus 3 minus 2 lambda plus 1 into minus 9 minus 2 plus 1 into 3 lambda minus 1. So therefore minus 3 minus 2 lambda minus 9 minus 2, this is minus 11, plus 3 lambda minus 1 equal to 0. Therefore 3 lambda minus 2 lambda is lambda. Minus 3 minus 11 minus 14 minus 14 minus 1 is minus 15. Take on other side. So lambda is 15. Now in this question, position vectors of 4 points are given. Here these are position vectors of 4 points. So that means, and we want to show that these 4 points are coplanar. All 4 points lie in a same plane. So to show that 4 points are coplanar, see A, B, C, these are coplanar points. To show that 4 points are coplanar, what we will show? We will show that vector AB, vector AC and vector AD are coplanar. To prove that these 4 points are coplanar, we have to prove that these vectors are coplanar. So here we will use rule for coplanarity. So we will show that box product of these 3 vectors is 0. So let me name here. We say this is position vector of A, position vector of B, position vector of C and position vector of D. So let given vectors are position vectors of points A, B, C and D respectively. So we can also say that A is 4 coordinates of A 4, 8, 12, coordinates of B 2, 4, 6, coordinates of C 3, 5, 4 and coordinates of D 5, 8, 5. We can also this statement we can also put by this method also. So these are position vectors of these 4 points A, B, C, D. So coordinates of A, B, C, D are taken by these triplets. So here now vector AB is 2 minus 4 times I, that is minus 2I. See, position vector of B minus position vector of A, position vector of B minus position vector of A. So 2 minus 4 times I plus 4 minus 8 times, that is minus 4 times J, plus 6 minus 12, that is minus 6 times K. You can also calculate from these coordinates 2 minus 4, then 4 minus 8, 6 minus 12. Similarly, vector AC is AC. So 3 minus 4 is minus 1I, 5 minus 8 minus 3J, 4 minus 12 minus 8K. AC 3 minus 4, 5 minus 8, 4 minus 12. Then vector AD is D minus A. So 5 minus 4 is 1I, 8 minus 8 is 0J, 5 minus 12 is minus 7K. Now therefore box product of AB, AC and AD, calculating box product of scalar triple product of these 3 vectors, components of vector AB, so minus 2, minus 4, minus 6, minus 1, minus 3, minus 8, 1, 0, minus 7. So minus 2 into, so here 21 minus 0, plus 4 into 7 minus 8, that is plus 8, plus minus 6 into 0 minus 3, that is plus 3. So this is equal to minus 42, this is 8 plus 7, 15 into 4 plus 60, this is minus 18. So this is 0. So box product is 0. Scalar triple product of these three vectors is 0. Therefore, vector AB, vector AC and vector AD are coplanar. And three vectors are coplanar. It is possible only when 4 points A, B, C, D are coplanar. Therefore, points A, B, C and D are coplanar points. So that vectors A, B and C are coplanar if vector A plus vector B, vector B plus vector C and vector C plus vector A are coplanar. So here this is given. Here given that vector A plus vector B, B plus C and C plus A, these vectors are coplanar. It is given. Vectors are coplanar, so their box product will be, this is box product of these three vectors. It is equal to 0 because vectors are coplanar. And we want to show that these vectors A, B and C are coplanar. And to show that these vectors are coplanar, we have to show that their box product is 0. If we can prove box product of these three vectors 0, that means they are coplanar. So beginning from this statement, we are going to derive this statement. Now, coming back on this step, box product. So by definition of this scalar triple product, this is first vector dot cross of these two vectors B plus C cross C plus A. Box product of x, y, z is 0. That means x dot y cross z. Next step is, first of all, we calculate this cross product. So say A plus B, keep as it is. Now here, cross product is distributive over addition. So this vector I am taking cross with C and with A. Cross product is distributive over addition. So B plus C cross C plus B plus C cross A equal to 0. X cross Y plus X cross Z, like that. Cross product is distributive over addition. Therefore, vector A plus vector B dot, now here again cross product is distributive over addition. So B cross C plus C cross C without changing order, because cross product is not commutative. So B cross C, so B is on left, C is on right side, so keep as it is, as they are. B on left, C on right, plus C cross C. Similarly, B cross A, B is on left, A is on right side, so B cross A plus C cross A. B cross A, so B cross A. Now this cannot be written as A cross B. Cross product is not commutative. Then, now here This is 0 vector. We can put here 0. Or if you keep as it is, then also finally we will get required answer. Let me put here 0. A plus B dot B cross C plus, this is 0 vector, C cross C is 0 vector, plus B cross A plus C cross A is 0. Now dot product is distributive over addition. Here now we are having 3 vectors. 0 vector is nothing. So first of all, cross product with A. So taking cross with A, dot product with A. So it will be A dot B cross C, A dot B cross C, then A dot B cross A plus then A dot C cross A, A dot C cross A. So turn of A is over. Now turn of B, B dot B cross C, B dot B cross C, B dot B cross A, B dot B cross A, B dot C cross A, B dot C cross A. This is equal to 0. Now say A dot B cross C, A dot B cross C, it is box product of A, B, C. Second term plus box product of vector A, vector B, vector A. Third term box product of vector A, vector C, vector A. Fourth term box product of vector B, vector B, vector C. Fifth term box product of vector B, vector B, vector A. And last step box product of vector B, vector C, vector A. This is equal to 0. So therefore box product of A, B, C. See here we can also separate these vectors by comma, or if you don't keep comma, then also it is allowed. Now see here repetition of vectors. If repetition is seen, its value is 0. Here repetition of vector A, so value is 0. Here repetition of B, value is 0. Repetition of B, value is 0. Plus. Now here no repetition in last. So last we are putting this as, say, now this can be written as, I am making similar as first term. Here starting is from B, so I am starting from A, so this is A. Now look the chain, after A what comes? B. So after A B comes, then what comes? C, equal to 0. So we are doing by this way. So that means 2 times vector A, vector B, vector C, box product of these 3 vectors 0. Therefore box product is 0, so required result is proved.